These are 18 stars that break the rules astronomers thought were unbreakable, and nearly every single one of them was caught doing it, almost by accident. A star that looked older than the universe itself. A star built from almost nothing, missing the one element that should define its age. A second star, discovered years later, missing a completely different set of ingredients, so thoroughly that researchers flat out titled their own paper about it, a star that should not exist. A star so massive, it blows straight past the theoretical ceiling on how big a star is even allowed to get. A star so bright, it should have already destroyed itself, sitting right at the edge of its own physical limits for 2 centuries and counting. A star that exploded and kept living anyway. A star that seems to be feeding on rare, radioactive elements that shouldn't be able to exist on its surface at all. A star with a dead neutron core buried inside it, if the strangest reading of its light turns out to be right. A star whose flickering got so bizarre that professional astronomers seriously entertained the idea of an alien-built megastructure. A star that nearly convinced the entire astronomical community it was about to go supernova, live, in real time. A dead star, spinning fast enough and magnetized hard enough to behave like something that should only be possible for a neutron star. A neutron star that unleashed, in a fifth of a second, more energy than our sun releases in 250,000 years. Another neutron star spinning over 700 times every single second, while carrying more mass than physics thinks a neutron star should be able to hold together. A star fired clean out of the galaxy by a black hole, never coming back. The single most distant star human eyes have ever detected, caught only because of a trick of gravity itself. Stars that look decades younger than everything around them because they fed on a companion. A pair of stars that astronomers confidently predicted would collide and explode for the entire world to see, right on schedule, and then simply didn't. And finally, stars that might not be powered by nuclear fusion at all, but by something we've never even directly detected in a laboratory. 18 strange objects, one thread connecting all of them. Each one forced scientists to go back, look harder, and figure out how something that shouldn't exist actually does, or in one case, how something that seemed certain to happen simply never did. If that sounds like your kind of rabbit hole, stick around for all 18, and go ahead and hit subscribe before we start, because there's a lot more of this coming. Let's start with the one that basically invented this whole idea of an impossible star, because for a while, it genuinely looked like the universe had a math problem it couldn't explain away. In the constellation Libra, roughly 200 light-years from where you're sitting right now, there's a star that doesn't look like much through an amateur telescope. You'd never spot it with the naked eye. Astronomers had actually been logging its position for over 100 years before anyone understood what it truly was. And what they eventually figured out is the reason it now carries a nickname instead of just a catalogue number. They call it Methuselah, after the man in the Bible said to have lived 969 years, and the name turned out to be almost too fitting. In the year 2000, using data from the European Space Agency's Hipparcos satellite, a team of astronomers calculated this star's age and landed on a number that shouldn't have been possible under any accepted version of cosmology: 16 billion years old. The issue isn't that stars can't be old. Genuinely ancient stars are known and accepted throughout the galaxy. The issue is that the universe itself, according to the best available models, is only 13.8 billion years old, which means a star that predates the birth of everything isn't just an oddity, it's a direct contradiction, the kind of finding that either overturns a heavily tested theory or means somebody, somewhere, measured something wrong. Howard Bond, an astronomer at Pennsylvania State University who became the central figure in chasing this problem down, called the discrepancy exactly what it was. It's a serious discrepancy. And it was serious precisely because the Big Bang model isn't a loose guess. It's been confirmed across cosmic microwave background radiation, the expansion rate of space, and the ratios of light elements formed in the earliest moments of the universe. Dozens of independent lines of evidence, all converging on the same age. So when one star's calculated age came in nearly 2 billion years past that boundary, the obvious next move wasn't to question the Big Bang, it was to question the measurement. Here's the part that makes this such a good entry point into how stellar age actually gets calculated in the first place. You can't just look at a star and read its age directly. Astronomers work backward from indirect clues, and the single most important one is distance. Know exactly how far away a star sits, and you can calculate its true, intrinsic brightness, because you know precisely how much its light has faded on the long trip to your telescope. That intrinsic brightness is one of the biggest levers in age calculations, because for a given stellar type, the brighter the true output, the younger the star tends to be. Get the distance slightly wrong, and the age estimate can swing by billions of years. So starting in 2003 and stretching all the way to 2011, Bond's team assembled 11 separate sets of observations using the fine guidance sensors aboard the Hubble Space Telescope, chasing something called the parallax effect, the tiny apparent shift in a star's position against the background sky caused by Earth's own orbit. It sounds simple. Executing it with the precision this problem demanded is brutally hard. What they landed on was a revised age of 14.46 billion years. Still technically older than the universe, but now carrying an uncertainty of plus or minus 800 million years, which meant the number could, for the first time, be squeezed into agreement with cosmology if you leaned toward the younger edge of that range. Bond flagged another clue buried in the star's light, an unusually high ratio of oxygen to iron, and because oxygen wasn't abundant in the very early universe, that chemical fingerprint nudged the estimate younger still. It wasn't a full resolution, it was a narrowing, one careful step at a time. That's really the whole story of Methuselah, incremental and stubborn instead of clean and instant, and it kept unfolding for another decade. A follow-up study in 2014 pulled the number down again, to 14.27 billion years, still over the line, barely. Then in 2015, an entirely different tool entered the picture, the European Space Agency's Gaia spacecraft. Purpose-built to map the positions and distances of stars with extraordinary precision, Gaia placed Methuselah at about 190 light-years out, and using that sharper distance, the age came out to 13.7 billion years, plus or minus 700 million. For the first time, the number sat comfortably inside the accepted age of everything. The paradox that had made international headlines for over a decade quietly dissolved, not because of new physics, but because of better rulers. And even that wasn't the final word. A 2021 study from the Australian National University, led by researcher Jianling Tang along with Meredith Joyce, used a completely different technique, an interferometer called PAVO, mounted on the Chara Array in California, which measures a star's physical size directly instead of inferring it from brightness. That pushed the estimate down even further, to 12 billion years, with a mass just under our own sun's. So, depending on which paper you cite, Methuselah is somewhere between 12 and nearly 14 billion years old, which sounds like a wide spread until you remember it used to be flatly, mathematically impossible. Physicist Robert Matthews of Aston University in Birmingham, who wasn't part of the original team, but weighed in publicly, offered the reminder that's really the moral of the whole story. Like all measured estimates, it is subject to both random and systematic error. Methuselah remains, even with its headline number walked back, one of the oldest stars with a well-determined age anywhere in the Milky Way, and one of the closest surviving relics of the early universe you could point a backyard telescope at tonight. From a star with an impossible age to a star with an impossible absence, because what makes our next case strange isn't what's there, it's what's missing entirely. In 2014, a team working with the SkyMapper Southern Sky Survey in Australia was combing through the light of 60 million stars, hunting for anything with an off-color spectral signature, the kind of subtle clue that might point to something ancient hiding in plain sight. One star stood out immediately, its formal catalogue name, SMAS J03130.36-670839.3, is such a mouthful that astronomers just shortened it to SM0313, and it sits inside our own galaxy's halo, in the constellation Hydrus, a relatively close 6,000 light-years from Earth. Lead scientist Stephan Keller of the ANU Research School of Astronomy and Astrophysics, working with MIT's Dr. Anna Friebel, took high-resolution follow-up spectra using the 6.5-meter Magellan Clay telescope in Chile, and what they found, published in the journal Nature, became one of the most talked-about stellar discoveries of the decade. To understand why, you have to know how astronomers use the word metal. In everyday speech, that means something like iron or gold. In astronomy, it means almost anything heavier than helium, because hydrogen and helium are what the universe consisted of right after the Big Bang, before any stars had lived, died, and scattered heavier elements forged in their cores back out into space. Metallicity, then, works as a rough clock. Low metal content usually signals an old star, born before generations of stellar death had enriched the surrounding gas. High metal content usually signals a younger star, built from material that had already cycled through several stellar lifetimes. SM0313 doesn't just have low metallicity, it has none that anyone can detect at all. Its spectrum shows no iron lines whatsoever, at a level astronomers calculate to be at least 10 million times less iron than the Sun, with one estimate placing the true upper limit as low as 15 million times less. The only strong signals in its light come from hydrogen and carbon, plus a couple of lines that turned out to be contamination from Earth's own atmosphere. Every other element that should normally register in a star's chemical fingerprint sits below the threshold of detection. Freible was refreshingly candid about the limits of what that tells scientists. Truthfully, we don't actually know how old SM0313 is. This is because, sadly, we can't determine a specific age of these kinds of objects. However, the chemical composition of SM0313 tells us that it is a second-generation star in the universe, which naturally makes this star nearly as old as the universe itself. That phrase, second generation, is the key to the whole discovery. The very first stars ever to exist, what astronomers call population 3 stars, were built purely from primordial hydrogen and helium, because nothing else existed yet. Those first stars lived brief, violent lives, and when they died in supernovae, they were expected to scatter iron and other heavy elements into the surrounding gas. The next generation of stars, born from that enriched material, should carry the fingerprint of that iron pollution. SM0313 is unmistakably a second-generation star, built from the wreckage of one of those very first stellar deaths, and researchers calculated that the single ancient supernova responsible came from a progenitor roughly 60 times the mass of the Sun. Instead of the iron signature theory predicted, though, SM0313 shows almost nothing. Keller summed up the stakes directly. This is the first time that we've been able to unambiguously say that we've found the chemical fingerprint of a first star. What this star has enabled us to do is record the fingerprint of those first stars. The leading explanation researchers arrived at is that the ancient supernova powerful enough to blow lighter elements like carbon out into space was too weak to fully eject the iron formed deep in its own core, and that iron simply fell back inward, swallowed rather than scattered. It's a star that exists because an explosion some 13 billion years ago somehow never finished the job every model expected it to. From a star built on an absence to a second star discovered a few years later that's missing an entirely different set of ingredients, so completely that the scientists who found it gave their own discovery paper a title that could serve as the name of this whole list. In September of 2011, astronomer Elisabetta Caffau and her colleagues, publishing in the journal Nature, announced a star found through the Sloan Digital Sky Survey, an automated telescope system at Apache Point Observatory in New Mexico that had spent a decade methodically cataloging the night sky. The star, formerly named SDSS J102915+172927 and quickly nicknamed Caffau's star, sits in the constellation Leo, is smaller and hotter than our Sun, and would have been utterly forgettable if Sloan's software hadn't flagged something odd buried in its spectrum. At the time of its discovery, it held the record for the lowest metallicity ever measured in any star, with a total metal content less than 7/10 of the Sun's, meaning it's built almost entirely out of the same raw hydrogen and helium the universe started with, at 13 billion years old, making it one of the most ancient stars known in the galaxy. Here's where it crosses over from remarkable into genuinely puzzling. Existing theoretical models had made a fairly confident prediction about how the very first low-mass stars, stars roughly the size of our own Sun, rather than the towering, short-lived giants of population 3, were able to form at all in the metal-starved early universe. The idea was that carbon and oxygen, even in tiny trace amounts, were essential, because those two elements are unusually efficient at radiating away heat from a collapsing gas cloud, and a cloud has to shed heat effectively in order to fragment down into something star-sized, rather than just collapsing straight into one enormous object. CAFO's star should have needed exactly that kind of carbon and oxygen boost to exist as a small, sun-like star at all. Instead, it turned out to be deficient in carbon, nitrogen, and oxygen alike, and stranger still, it showed no detectable lithium whatsoever, a complete absence of an element that shows up reliably in essentially every other metal-poor star of comparable age, since lithium is thought to have been produced directly during the Big Bang itself, and should, in theory, persist at some measurable level almost everywhere. An Astrobytes analysis summarizing the discovery paper gave it the title that says everything about how seriously the finding was taken: a star that should not exist. A piece covering the discovery for Time magazine put it even more bluntly. Cosmic theory says CAFO's star is impossible, yet it's shining out there all the same. Researchers have proposed a few different ways to square the star's existence with the models. One line of research, led by astrophysicist Raffaella Schneider, suggests that trace amounts of cosmic dust, rather than carbon and oxygen gas cooling, may have been what allowed the collapsing cloud that formed CAFO's star to shed enough heat to fragment into something this small, effectively finding a second, dust-based pathway to low-mass star formation that the original models hadn't accounted for. Other researchers have proposed instead that the star isn't quite what it first appeared to be, that it might actually be a slightly more evolved subgiant rather than a true main-sequence dwarf, which would change how its missing lithium gets interpreted, since lithium can be dredged down and destroyed inside a star as it evolves, rather than simply being absent from birth. Data released later from the European Space Agency's Gaia mission ultimately confirmed the simpler picture, that CAFO's star genuinely is a small dwarf star, not a subgiant, which puts the missing lithium problem right back on the table unresolved. More than a decade after its discovery, astronomers still don't have full agreement on exactly how a star this small, this old, and this chemically empty ever managed to form in the first place. Only that, whatever process allowed it, it clearly worked. Now, from a star that shouldn't have been able to form at all, to a star that simply shouldn't be as big as it is, because somewhere in the Large Magellanic Cloud sits an object that broke the theoretical rulebook on how massive a star is even allowed to become. Deep inside the Tarantula Nebula, a sprawling star-forming region in the Large Magellanic Cloud, roughly 160,000 light-years away, sits a dense stellar cluster called R136. For decades, astronomers assumed the intense ultraviolet glow coming from its core had to be a single, almost impossibly massive star, because nothing else seemed capable of producing that much light. Hubble Space Telescope observations eventually resolved that glow into a tight cluster of individual stars instead, but the brightest one at its center, catalogued as R136A1, turned out to be a monster in its own right. In 2010, a team led by Paul Crowther of the University of Sheffield, using archival Hubble and Very Large Telescope spectroscopy, calculated that R136A1 had a present-day mass somewhere around 265 times that of our Sun, with an estimated birth mass as high as 320 solar masses. Here's why that number is a genuine problem rather than just a big one. Standard models of how stars form by pulling in and accreting material from a surrounding molecular cloud predict a natural upper limit on stellar mass, because at some point, a growing star becomes so luminous that its own radiation pressure should blast away any remaining infalling gas before the star can get any bigger. The simplest versions of those models cap out as low as 40 solar masses. More complex models allow for more, but an empirical limit around 150 solar masses had become the widely accepted ceiling in the field. R136A1, sitting at nearly double that figure, clearly exceeds it, which forced astronomers to seriously consider that stars this massive might not form through simple accretion at all, but through violent mergers of already massive binary stars colliding and combining into one. The exact number has bounced around since, in a pattern that should feel familiar by now if you've been following this list. In 2022, astronomer Venu Kalari of NOIR Lab led a team using the Gemini South Telescope's Zorro imaging instrument in Chile to capture the sharpest image of R136A1 ever taken, precise enough to finally separate its light cleanly from several close stellar neighbors that had been blurring into its measurements. That refined image brought the mass estimate down to somewhere between roughly 170 and 230 solar masses. Kalari summarized the result plainly. Our results show us that the most massive star we currently know is not as massive as we had previously thought. This suggests that the upper limit on stellar masses may also be smaller than previously thought. Even at the lower end of that revised range, R136A1 still comfortably holds the title of the most massive star known anywhere in the universe, and it still exceeds the old accepted ceiling. The mass has shrunk. The mystery of how something crosses that line at all hasn't gone anywhere, which brings us to a star that raises the opposite question. Not how something got so big, but how it hasn't yet torn itself apart. In the southern constellation, Carina sits Eta Carinae, a massive binary system whose dominant member is a class of star called a luminous blue variable, blazing at roughly 4 million times the brightness of our Sun, and carrying, along with its companion, a combined mass north of 100 solar masses. Astronomers describe Eta Carinae as sitting dangerously close to something called the Eddington limit, the theoretical point at which a star's own outward radiation pressure becomes strong enough to overpower the inward pull of its own gravity. Cross that line, and a star should, in principle, start blowing itself apart from the inside, unable to hold its own outer layers in place. Researchers studying the star's physics describe its Eddington parameter as sitting at 0.9 or higher, which is about as close to that edge as a star can get without simply losing the fight entirely. Eta Carinae has actually shown, on at least one occasion, exactly what happens when it gets pushed past that edge. Starting in the 1830s and continuing for roughly 2 decades, the star went through what astronomers now call the Great Eruption, a catastrophic mass loss event during which it may have ejected somewhere between 10 and 20 solar masses of material directly into space, an amount of matter comparable to what an entire supernova explosion throws off, except Eta Carinae did it while staying alive. The event was so violent, it briefly made the star one of the brightest objects in the night sky, and it carved out the 2-lobed cloud of expelled gas, now known as the Homunculus Nebula, which still surrounds the star today. What actually triggered an eruption that extreme, on a timescale that fast, remains a genuinely open question in stellar physics. Researchers have proposed several competing mechanisms, from pulsation-driven instabilities deep in the star's envelope to gravitational energy released by mass being dumped onto its binary companion, and none of the existing models fully account for both the sheer amount of material ejected and the speed at which it happened. As one comprehensive review of luminous blue variables put it, after walking through the leading theoretical explanations one by one, the true nature of the LBV phenomenon remains as yet elusive. Astronomer Roberta Humphreys of the University of Minnesota has noted that any star above roughly 40 to 50 solar masses will likely pass through this kind of unstable phase eventually, which means Eta Carinae isn't some singular freak of nature, it's a preview of a phase every sufficiently massive star has to survive, or doesn't, on its way toward an eventual supernova that could, by current expectations, come at almost any time. Now, from stars that shouldn't be able to hold themselves together at all, to an entire class of stars caught red-handed feeding on their neighbors to stay young. Because it turns out, cosmic vampirism isn't science fiction, it's a documented stellar process with a name. In 1953, an astronomer named Alan Sandage was studying the globular cluster Messier 3 when he noticed something that didn't fit. Globular clusters are enormous, ancient swarms of stars, hundreds of thousands of them bound together by gravity, and crucially, every star inside a given cluster forms at roughly the same time, out of the same collapsing cloud of gas. That means you can use a cluster like a control group. Line the stars up by color and brightness, and you get a clean picture of exactly how a population of stars that age evolves together. except Sandage found a handful of stars in Messier 3 that were bluer and hotter than they had any right to be, stars that looked like they belonged to a much younger population entirely, sitting right there among their multi-billion-year-old siblings. He called them blue stragglers because they looked like laggards, stars that had somehow fallen behind the normal aging process. The name stuck, and so did the mystery, for more than 70 years. The globular cluster Messier 30 became one of the best studied examples. It's located about 28,000 light-years from Earth, a swarm of several 100,000 stars packed into a region only 90 light-years across, discovered by Charles Messier back in 1764, and formed roughly 13 billion years ago. Nearly every star in it should be old, cool, and red. Yet astronomers using the Hubble Space Telescope found two distinct populations of blue stragglers inside Messier 30, and traced them to two entirely different, equally strange origin stories. One group formed through direct stellar collisions, two low-mass stars in an overcrowded cluster core, physically slamming together, merging their fuel and mass into a single hot, rejuvenated star. The other group formed through something researchers openly call vampirism, a pair of stars locked in a tight binary, where the smaller, less massive star slowly siphons fresh hydrogen off its larger companion, feeding on it until it heats up, turns blue, and starts behaving like a star at an earlier stage of life entirely. Researchers even traced both populations in Messier 30 back to a single violent event in the cluster's history, called core collapse, that happened a few billion years ago. One astronomer working on the study put the strangeness in the plainest possible terms. It's like seeing a few kids in the group picture of a rest home for retired people. For decades, this stayed a genuine open puzzle, collision or companion. Which mechanism actually dominates? Then, more recently, two major studies came at the question from opposite directions and largely converged on an answer. One team used the James Webb Space Telescope to analyze more than 3,400 blue straggler stars spread across 48 separate globular clusters in the Milky Way, and their conclusion, published in the journal Nature Communications, stated the underlying problem about as directly as a scientific paper ever does. Blue stragglers are anomalously massive core hydrogen-burning stars that, according to the theory of single-star evolution, should not exist. A separate Hubble-based study confirmed the pattern from another angle entirely, finding that blue stragglers cluster overwhelmingly in binary systems, and that the environment around those binaries matters enormously. Astronomer Enrico Vesperini of Indiana University explained why. Crowded star clusters are not a friendly place for stellar partnerships. Where space is tight, binaries can be more easily destroyed, and the stars lose their chance to stay young. In looser, less crowded clusters, binary vampirism survives long enough to keep producing these rejuvenated stars, and the research suggests that mechanism, not violent collisions, does the majority of the work galaxy-wide. Vampire stars, it turns out, are simply more common than head-on collisions, which is either reassuring or unsettling, depending on how you feel about being told the universe runs on the stellar equivalent of feeding off your neighbor to stay looking young. If a star quietly feeding on its neighbor for a bluer complexion sounds strange, our next case is stranger still, because this one isn't stealing hydrogen. It's carrying elements that, chemically speaking, have almost no business existing on a stellar surface at all. About 370 light-years away, in the constellation Centaurus, sits a star discovered in 1961 by Polish-American astronomer Antoni Przybylski. HD 101065, or Przybylski's star, belongs to a category astronomers call chemically peculiar, stars whose spectra show wildly unusual abundances of certain elements. Przybylski identified barium, strontium, and all 15 rare earth elements sitting in the star's outer layers at concentrations 1,000 to 10,000 times higher than in our own sun, alongside unusually low levels of iron and nickel. That alone would make it an interesting object. What makes it something else entirely is what later research found layered on top of that: actinides, a family of heavy, radioactive elements running from actinium through plutonium and beyond on the periodic table, elements whose longest-lived isotopes have half-lives measured in mere years or decades. Przybylski's star is, according to researchers, the only known star in the sky carrying detectable traces of them. That fact alone should be impossible on its face. If an element has a half-life of a year, and the star is thousands or millions of years old, that element should have decayed into something else long, long ago, unless it's somehow being continuously replenished. Jason Wright, an astronomer at Penn State who has called Przybylski's star his favorite astrophysical enigma, has spent years trying to understand what's actually happening in its atmosphere, and even the basic act of reading its spectrum is a genuine challenge. As Wright has put it, describing the sheer density of overlapping spectral lines, some people say there are so many chemical indicator lines in the star's light that you really can't tell what you're looking at. One proposed explanation involves something called photolevitation, a process where radiation pressure inside a slowly rotating, magnetically stable atmosphere physically lifts certain heavier elements up toward the surface while letting others sink, concentrating exotic material in a thin outer layer and making the star's true bulk composition almost impossible to read directly from its light. And Przybylski's star really is an exceptionally slow rotator. A 2018 study using the high-accuracy Radial Velocity Planet Searcher instrument on a 3.6-meter telescope in Chile measured its rotation period by tracking its magnetic field and found the star takes nearly 2 centuries to complete a single spin on its axis. But levitation alone doesn't fully explain the actinides, because it doesn't explain how they're being replenished as they decay. That's where the more exotic proposals come in, and researchers genuinely disagree about which one is right. One hypothesis, explored by a Ukrainian research team and discussed in later papers, suggests the star might have an unseen companion, a neutron star acting as a gamma-ray pulsar, irradiating the outer atmosphere of Przybylski's star and continuously synthesizing short-lived heavy elements right there on its surface through exotic nuclear reactions. The problem with that idea, as researchers themselves acknowledge, is straightforward. Nobody has found a neutron star anywhere near it. No orbital wobble in the spectroscopic data confirms a hidden companion at all. A separate and even stranger hypothesis, proposed by physicist Vladimir Dzuba at the University of New South Wales and his colleagues, suggests something bolder, that the actinides are decay products of undiscovered super-heavy elements sitting in a theoretical, unconfirmed region of the periodic table called the Island of Stability. Elements heavier than anything ever created or observed on Earth, which could persist for millions of years before slowly decaying down into the shorter-lived actinides astronomers are actually detecting. Neither explanation has been confirmed. Both remain live hypotheses, decades after Przybylski first logged the star's odd spectrum, and the honest scientific answer right now is that nobody fully knows what Przybylski's star is doing, only that whatever it is, it's happening on the surface of an ordinary-looking point of light, 370 years away, quietly hosting elements a physics textbook would tell you shouldn't survive there at all. From a star with an unexplained atmosphere, to a star that might be hiding something far stranger underneath its surface entirely, the crushed remains of another star, buried alive at its core. In 1975 and 1977, physicist Kip Thorne and astronomer Anna Zitkoff proposed a genuinely strange kind of hybrid object, a star that looks, from the outside, like an ordinary red supergiant, but that secretly contains a neutron star packed inside its core. The formation story is almost as violent as it sounds. In a close binary system, one star explodes as a supernova and collapses into a neutron star, one of the densest objects in the universe, an object so dense that a teaspoon of its material would weigh billions of tons. If that neutron star then spirals inward through unstable mass transfer, or gets kicked by the asymmetry of its own supernova explosion directly into its companion, it can end up literally inside the envelope of the surviving giant star, orbiting deep within its outer layers, rather than orbiting it from a distance. The result, if it forms and survives, is called a Thorne-Zitkoff object, and for nearly 40 years after it was first proposed, it stayed exactly what that description makes it sound like, a compelling idea on paper, with zero confirmed examples anywhere in the sky. That changed, or seemed to change, in 2014. A team led by Dr. Emily Levesque of the University of Colorado Boulder used the 3.5-meter telescope at Apache Point Observatory in New Mexico to study 24 red supergiants in the Milky Way, and the 6.5-meter Magellan Clay Telescope in Chile to study dozens more across the large and small Magellanic Clouds, nearby satellite galaxies of our own. When the spectrum of one particular star, HV 21112, sitting in the small Magellanic Cloud, roughly 200,000 light-years away, first came up on screen, the reaction from the team was immediate. Nydia Morell, of the Carnegie Observatories, put it simply, "I don't know what this is, but I know that I like it." When LeVecq's team looked closer at the star's subtle spectral lines, they found unusually high abundances of molybdenum, rubidium, lithium, and calcium, a specific combination theorized to arise only from a rare, exotic nuclear process called the interrupted rapid proton process, one that can only occur when hydrogen burns at the extreme temperatures found where a stellar envelope presses directly against a neutron star's surface. Combined with the star's unusually high luminosity, it matched the theoretical fingerprint of a Thorne-Zitkoff object closely enough that LeVecq's team announced HV 2112 as the strongest candidate ever found. Anna Zitkoff, who had proposed the entire concept 4 decades earlier, reacted with the kind of relief that comes from waiting that long to be taken seriously. "I am extremely happy that observational confirmation of our theoretical prediction has started to emerge. Since Kip Thorne and I proposed our models of stars with neutron cores, people were not able to disprove our work." LeVesque was careful about the stakes involved, telling reporters at the time, "If HV 2112 is found to be a bona fide TZO, this would have huge implications. It could offer the first solid evidence for a completely different model of how stars' interiors can work." The story didn't end there, and this is where it gets genuinely contested rather than neatly resolved. In 2018, a separate team led by Emma Bisa took another close look at HV 2112 and directly challenged the original claim, arguing there was no clear evidence of the unusual calcium abundance the original paper had relied on, and that most of the star's spectrum looked like an entirely ordinary red supergiant, aside from a modest excess of lithium. Other researchers proposed competing explanations entirely, suggesting HV 2112 might instead be what's called a super-asymptotic giant branch star, a different and much more mundane type of object, capable of producing some, though not all, of the same chemical signatures without any neutron star involved at all. Later work using precise position data from the European Space Agency's Gaia satellite confirmed HV 2112's location and motion are consistent with it belonging to the small Magellanic Cloud, which at least settled the argument over where the star actually is, even as the argument over what it is remains unsettled to this day. As of the most recent research on the subject, no Thorne-Zitkoff object has been universally agreed upon and confirmed. HV 2112 remains the leading candidate with an asterisk next to its name, and a second possible candidate, HV 11417, also sits in the small Magellanic Cloud, awaiting its own closer look. It's a rare case in this list where the mystery isn't really about what the star is doing that's strange, it's about whether astronomers can even agree on what they're looking at in the first place. From a star that might be hiding a dead star inside it, to a star that had the entire internet convinced, for a genuinely serious stretch of time, that it might be surrounded by an alien-built power station. In October of 2015, astronomer Tabetha Boyajian at Louisiana State University was looking at data from NASA's Kepler Space Telescope, brought to her attention through a citizen science project called Planet Hunters, where ordinary volunteers scan telescope data for the tiny brightness dips caused by planets passing in front of distant stars. A normal planetary transit dims a star by around 1% or less, in a clean, regular, repeating pattern. The star, catalogued as KIC 8462852, was doing something else entirely. Its brightness dropped by as much as 22%, an enormous, unprecedented dip for anything short of another star passing in front of it, and the dimming events showed no regular pattern at all, arriving unpredictably, at different depths, at different times, ruling out a simple orbiting planet immediately. The star sits roughly 1,000 to 1,470 light-years away, in the constellation Cygnus, and is otherwise fairly ordinary, about 50% bigger than our Sun and roughly 1,000 degrees hotter. What it was doing with its own light was anything but ordinary, and it quickly picked up two nicknames: Tabby's star after its discoverer, and Boyajian's star, its more formal namesake. Astronomers threw out one hypothesis after another: a swarm of orbiting comets. A collision that had shattered a planet into an irregular debris cloud still settling into its own dust ring, material drifting through our own solar system, coincidentally passing in front of the line of sight. And then, in a 2015 paper, titled with a question that became genuinely famous in astronomy circles, "Where's the flux?" Penn State astronomer Jason Wright and collaborator Stein Sigurdsson raised, seriously and cautiously, the idea that the dimming pattern was at least consistent with what you might expect from an enormous artificial structure built by an advanced civilization to harvest energy from the star, something like a partial Dyson swarm. Wright and Sigurdsson were careful in how they framed it, noting in their paper that because Boyajian's star's behavior is so rare, the correct explanation is probably going to be something inherently unlikely too, not necessarily aliens, just something genuinely uncommon in nature. But the idea was out, and it spread everywhere, turning an obscure Kepler data point into international news and drawing serious follow-up attention from SETI researchers hunting for any radio or laser signal that might back the idea up. None ever showed up. What actually solved it, eventually, was Boyajian herself, running one of the more unusual funding campaigns in modern astronomy. She launched a Kickstarter campaign that raised over $100,000 from more than 1,700 backers, funding continuous ground-based monitoring of the star through a network of telescopes so that the next time it dimmed, astronomers would be watching in real time through multiple colors of light simultaneously, rather than reconstructing the event after the fact from old Kepler data. That opportunity came in 2017, and the key test was simple in concept. If a solid, opaque object like a megastructure passed in front of the star, it would block every wavelength of light equally. If it was something more like a diffuse cloud of dust, it would block shorter, bluer wavelengths more strongly than longer, redder ones. Boyajian explained the logic plainly. If a solid, opaque object like a megastructure was passing in front of the star, it would block out light equally at all colors. The 2017 observations and a larger follow-up study involving more than 200 researchers, published on January 3, 2018, found exactly the uneven, color-dependent dimming pattern you'd expect from dust, not a solid structure, closing the door on the megastructure hypothesis for good. Boyajian summarized the anticlimactic but scientifically satisfying answer. Dust is most likely the reason why the star's light appears to dim and brighten. There was one more twist worth mentioning. In 2021, astronomers using the Keck Observatory in Hawaii, cross-checked against data from the Gaia satellite, confirmed that Boyajian's star actually has a faint, gravitationally bound companion star, a small red dwarf sitting about 880 astronomical units away, which may end up playing a role in explaining exactly where all that dust is coming from and why it behaves the way it does. The alien megastructure never panned out, but the star that inspired the idea remains, in the words of one astronomer who's tracked it for years, a case that drives me a little crazy, precisely because even with the biggest explanation ruled out, plenty of the smaller details are still not fully pinned down. From a star whose flickering fooled the public into thinking about aliens, to a star so famous and so close that its flickering briefly had professional astronomers wondering if they were about to watch a supernova happen in real time. Betelgeuse is one of the most recognizable stars in the night sky, the bright reddish-orange shoulder of the constellation Orion, a red supergiant so enormous that if it replaced our Sun at the center of the solar system, its outer surface would extend past the orbit of Jupiter. It's also a star widely expected to explode as a supernova at some point, astronomically speaking, soon, though soon in stellar terms could mean anywhere from tomorrow to 100,000 years from now. So when Betelgeuse started dimming dramatically in October of 2019, losing more than 2/3 of its normal brightness by mid-February of 2020, in a drop severe enough to notice with the naked eye, the astronomical community, and a fair amount of the general public along with it, spent months genuinely wondering whether they were watching the early warning signs of the star's death. Researchers scrambled to explain it. One early theory proposed a massive, cool star spot covering a wide swath of the star's visible surface. The actual answer, pieced together by a team led by astronomer Andrea Dupree of the Center for Astrophysics at Harvard and Smithsonian, using months of ultraviolet spectroscopic data from the Hubble Space Telescope, turned out to be almost as dramatic as an impending supernova, just not fatal. Beginning in September of 2019, Hubble detected dense, superheated material erupting from a large convective cell on the star's surface and surging outward through its atmosphere at roughly 200,000 miles per hour. Dupree described watching it happen in real time. With Hubble, we could see the material as it left the star's surface and moved out through the atmosphere before the dust formed that caused the star to appear to dim. Once that ejected material traveled far enough from the star's blistering heat, millions of miles out, it cooled enough to condense into an enormous cloud of dust, and that cloud, drifting directly across our line of sight, blocked light from roughly a quarter of Betelgeuse's visible surface. By April of 2020, the star had returned to its normal brightness, and follow-up imaging from other observatories later captured direct visual confirmation of the dust cloud itself, partially obscuring the star's disk. Betelgeuse wasn't dying. It had, in effect, coughed, violently enough to briefly convince half the astronomical world otherwise, and it remains exactly where it was, still waiting, on its own unknowable timeline, for the explosion everyone still expects eventually. From a star whose mystery played out entirely within our own galaxy, to one so far away that its own light took nearly 13 billion years just to reach us, and that we only ever caught sight of because of an extraordinary trick of gravity itself. In March of 2022, a team led by Dr. Brian Welch of Johns Hopkins University announced, in a paper published in the journal Nature, the discovery of the most distant individual star ever detected by human instruments, found through Hubble's Reionization Lensing Cluster Survey program. They nicknamed it Earendel, an Old English word meaning morning star. Under normal circumstances, a single star at this kind of distance would be utterly invisible, drowned out entirely, its light blending into the smudged glow of its entire host galaxy, the way millions of individual candles blur into one soft haze from miles away. Welch described exactly that limitation. Normally at these distances, entire galaxies look like small smudges, the light from millions of stars blending together. Earendel was only detectable at all because of an accident of cosmic geometry. A massive galaxy cluster, called WHL 013708, sits directly between Earth and Earendel's home galaxy, and that cluster's gravity is so immense that it physically warps the space around it, acting like a natural magnifying lens. Earendel's host galaxy, nicknamed the Sunrise Arc because the lensing effect stretched its light into a long, curved crescent, happened to line up along the single sharpest, most extreme point of that gravitational magnification, known as a caustic, boosting the star's brightness by a factor astronomers estimate at somewhere between 1,000 and 40,000 times, depending on the specific analysis. Welch compared the effect to something almost playful for such an extreme phenomenon, the way ripples on the surface of a swimming pool focus sunlight into bright, shifting patterns on the pool floor below. The numbers involved are genuinely difficult to hold in your head. Earendel sits at a redshift of 6.2, meaning its light was emitted when the universe was somewhere between 6 and 7% of its current age, roughly 900 million to 1 billion years after the Big Bang. That light has been traveling for approximately 12.9 billion years to reach us. But because the universe has kept expanding the entire time that light was in transit, the star's actual present-day distance, accounting for that expansion, is now an almost incomprehensible 28 billion light-years away. Dr. Victoria Straight, a postdoctoral researcher involved in the discovery, laid out the scale of it directly. When the light that we see from Earendel was emitted, the universe was less than 1 billion years old, only 6% of its current age. At that time it was 4 billion light-years away from the proto-Milky Way, but during the almost 13 billion years it took the light to reach us, the universe has expanded so that it is now a staggering 28 billion light-years away. It shattered the previous distance record for an individual star by a massive margin, a star nicknamed Icarus that had been observed at a much smaller redshift, around 1 to 1.5, corresponding to a time when the universe was already roughly a third of its current age. Welch himself admitted the team's first reaction to the data. "We almost didn't believe it at first. It was so much farther than the previous most distant, highest redshift star." Follow-up observations using the newer James Webb Space Telescope confirmed the detection and even managed to extract crude color information from Earendell's light. And researchers noted something else worth sitting with: that stars this massive very often have companions. Though Webb wasn't expected to be able to resolve one even if it exists, the two would simply be too close together to distinguish. And in a genuinely honest scientific footnote worth including, more recent analysis published in 2025 has reopened part of the question, examining whether Earendell's light more closely resembles a single star or a compact, unresolved star cluster, since the exact degree of gravitational magnification isn't perfectly known and leaves real room for ambiguity in exactly how large the source actually is. Even the record for the most extreme single point of starlight ever caught by human telescopes, in other words, comes with the same asterisk that runs through nearly every entry on this list: genuinely extraordinary, and still, in its finer details, an open question. From the most distant star ever detected, to a star close enough at home to throw its own violence directly at us. A star that got blown apart and simply refused to disappear. For most of the history of astronomy, a supernova has meant one thing above all else: an ending. When a white dwarf, the dense, burned-out core left behind by a sun-like star, gets pushed past a critical mass threshold, usually by pulling material off a companion star, it triggers a runaway thermonuclear reaction that tears the entire object apart in a matter of seconds. That's the textbook version of a Type 1a supernova, precise and uniform enough that astronomers use these explosions as cosmic measuring sticks, standard candles, to calculate distances across billions of light-years. Nothing is supposed to survive. The star simply ceases to exist. Except sometimes, something does survive, and the case that finally proved it happened in the sky in the year 1181. Chinese and Japanese court astronomers that year recorded a new star appearing overhead, one of only a small handful of supernovae ever documented before the invention of the telescope. For centuries, nobody connected that historical sighting to any physical object visible today. That changed in stages. In 2013, amateur astronomer Dana Patrick spotted a faint, unusual nebula while combing through survey images, a structure later named PAR 30 in his honor. It took until 2021 for a researcher at the University of Manchester to make the connection between that nebula and the historical sighting from 840 years earlier, and the object sitting at the center of PAR 30 wasn't nothing. It was a surviving fragment of the white dwarf that had supposedly detonated, still there, still burning, still active. Astronomers have taken to calling stars like this zombie stars. The technical term is a Type Wiax supernova, a rare cousin of the standard Type Ia explosion, and researchers estimate these events make up as little as 5% of Type Ia-style detonations. In a Type Wiax event, the explosion is weaker and incomplete, leaving a shattered but intact stellar remnant behind, rather than obliterating everything. In October of 2024, a team using three-dimensional mapping techniques, including work led by Caltech physics professor Christopher Martin with an instrument called KCWI, produced the first fully spatial reconstruction of the PA30 nebula and its surviving remnant. What they found was strange, even by the standards of a star that wasn't supposed to be there at all. The zombie star at the center of PAR 30 is now one of the hottest stellar objects known anywhere in the Milky Way, with a surface temperature estimated around 360,000 degrees Fahrenheit, and it's still throwing off powerful stellar winds, moving outward at speeds over 36 million miles per hour. The debris doesn't form a simple, even sphere the way older models assumed, instead streaming outward in an asymmetrical, almost flower-like pattern, filaments racing away at roughly 1,000 kilometers per second. Martin described the value of seeing it in 3 dimensions for the first time this way. A standard image of the supernova remnant would be like a static photo of a fireworks display. SN 1181 isn't alone either. A separate investigation, involving researchers including Saurabh Jha of Rutgers University, went back through years of archival Hubble images of a galaxy called NGC 1309 and found something remarkable. Pictures taken years before a 2012 event designated SN 2012Z that actually captured the exact system before it exploded, a blue companion star locked in orbit with a white dwarf, feeding it material. It marked the first time astronomers had identified the actual progenitor system of a Type Ia-style supernova in images taken before the blast happened. When they compared before and after, they found evidence the white dwarf hadn't been destroyed, and stranger still, the zombie star left behind was shining even brighter than it had before the explosion. Ryan Foley, who led related research comparing SN 2012Z to a much weaker case called SN 2008HA, which occurred in a galaxy 69 million light-years away, made the diversity of these events clear. SN 2012Z is one of the more powerful Type YAC supernovae, and SN 2008HA is one of the weakest of the class, showing that Type YAC systems are very diverse. Astronomers have now catalogued more than 30 of these events believed capable of leaving a surviving white dwarf behind, which means the zombie star at the heart of PAR 30 isn't a one-off curiosity. It's a member of an entire, quietly growing class of stars that exploded and simply kept going. From a star that came back from its own explosion to a star that got thrown clean out of the galaxy by something far more violent than any supernova. At the center of the Milky Way sits Sagittarius A, a black hole with a mass roughly 4 million times that of our Sun, and for a long time, its influence on nearby stars stayed mostly theoretical, predicted by the math, but rarely caught in the act. In 1988, astronomer Jack Hills proposed a mechanism for exactly how a supermassive black hole could violently interact with a binary star system, two stars orbiting each other, if that pair wandered too close. The black hole's tidal forces, Hills argued, could rip the binary apart entirely, capturing one star into a tight orbit while flinging its former partner outward at extraordinary velocity. For nearly 2 decades that stayed a prediction sitting quietly on paper. Then, in 2005, astronomers found the first real evidence it actually happens, when a star, catalogued as SDSS J090745.0+024507, was discovered moving at a radial velocity of roughly 853 kilometers per second, far beyond anything ordinary stellar motion could explain. It kicked off an entirely new subfield, the hunt for what astronomers now call hypervelocity stars, anything moving more than twice as fast as typical stars, well over 500,000 miles per hour. Over the following years, researchers found around 30 of them scattered across the galaxy. Then, in a discovery announced in late 2019, one of them broke every previous record and finally gave the Hills mechanism the kind of clean, direct confirmation astronomers had been chasing for decades. The star is called S5HVS1, found by lead researcher Sergei Kopasov of Carnegie Mellon University as part of a project called the Southern Stellar Stream Spectroscopic Survey, published in monthly notices of the Royal Astronomical Society. It sits in the constellation Grus, the Crane, a relatively close 29,000 light-years away, and it's a hot, young, main-sequence star, still actively fusing hydrogen, roughly 2 1/3 times the mass of our Sun. What makes it remarkable is how fast it's moving, 2.3 million miles per hour, or about 1,017 kilometers per second, close to 6 million kilometers an hour. For scale, a commercial jet cruises around 900 kilometers an hour. The fastest human beings have ever traveled, the Apollo 10 astronauts, hit just under 40,000 kilometers an hour swinging around the Moon. NASA's Parker Solar Probe, the fastest human-made object ever built, set a Guinness World Record at a little over 340,000 kilometers an hour in November of 2018. S5HVS1 is moving roughly 10 times faster than most stars in the Milky Way, and at the time of its discovery, it was recognized as the 3rd fastest star ever recorded. Tracing its trajectory backward, researchers calculated the star was ejected from the immediate vicinity of Sagittarius A about 5 million years ago, at a launch speed estimated around 4 million miles per hour. Its former binary partner, presumably, is still trapped somewhere deep in orbit around the black hole, having taken the losing side of the encounter. Dr. Ting Li of Carnegie Observatories and Princeton University called it exactly what it was. This is the first clear demonstration of the Higgs mechanism in action. Seeing this star is really amazing, as we know it must have formed in the galactic center, a place very different to our local environment. It is a visitor from a strange land. Kopasov added the broader context that made the find so significant. We have long suspected that black holes can eject stars with very high velocities. However, we never before had a clear association of such a fast star with the galactic center. And Dr. Douglas Boubert of the University of Oxford summed up the star's ultimate fate in a single line. S5 HVS1's velocity is so high that it will inevitably leave the galaxy and never return. Somewhere out there right now, that star is still going, carrying the scar of a violent encounter with a black hole toward the empty space between galaxies, on a one-way trip that began roughly around the same time our own ancestors first started walking upright. From a star that got launched across the galaxy by a black hole, to a dead star that started acting like something it technically isn't supposed to be able to become at all. Pulsars, in the traditional sense, are neutron stars, the ultra-dense collapsed cores left behind after a massive star's supernova, spinning rapidly and blasting out beams of radiation from their magnetic poles that sweep past Earth like a cosmic lighthouse. For decades, that definition seemed locked in, because generating that kind of beamed, pulsed emission was thought to require the extreme density and correspondingly extreme magnetic fields only a neutron star could produce. Then, in 2016, an international team led by Tom Marsh of the University of Warwick studied a binary star system called AR Scorpii, located about 380 light-years away in the constellation Scorpius, and found it pulsing in brightness with metronomic regularity every 1.97 minutes, across a staggering range of the electromagnetic spectrum, from radio waves all the way up into the ultraviolet. The system had actually been catalogued and casually observed for 40 years before anyone noticed what it was really doing, dismissed as an unremarkable variable star. What made AR Scorpii genuinely bizarre is that neither of its two stars is a neutron star at all. The system pairs a cool, low-mass, sun-like companion in a tight 3.5-hour orbit with a white dwarf, the dense, burned-out husk left behind by a star like our own Sun after it sheds its outer layers, ordinarily one of the more sedate objects in the stellar zoo. But this particular white dwarf is spinning rapidly and carrying a magnetic field up to 500 million Gauss, roughly 100 million times stronger than Earth's, strong enough to accelerate electrons to nearly the speed of light and fire them out as a genuine, focused beam, precisely mimicking the mechanism astronomers had assumed only neutron stars could produce. Follow-up research led by David Buckley confirmed the emission was strongly polarized in a pattern nearly identical to the famous Crab Nebula pulsar, one of the best-studied neutron star pulsars known, and concluded the entire system's dramatic brightening and dimming is powered by the white dwarf's own spin, gradually slowing down, bleeding rotational energy directly into light and radiation, the same fundamental mechanism that powers a neutron star pulsar, just running on a completely different and, by prior assumption, far too gentle an object. Researchers have since found at least one more candidate system showing the same behavior, but AR Scorpii remains the first confirmed case of what's now called a white dwarf pulsar, and it forced a quiet but real revision to what astronomers thought a pulsar was even allowed to be made of. From a dead star quietly rewriting the definition of a pulsar, to a dead star that, for a fraction of a second, outshone almost everything else in the observable universe combined. On December 27, 2004, a small, unassuming neutron star, roughly 20 kilometers across, sitting on the far side of the Milky Way in the constellation Sagittarius, released the single most powerful flash of energy ever recorded from outside our solar system. The object, catalogued as SGR 1800620, belongs to a class of neutron star called a magnetar, meaning it carries a magnetic field so extreme it's measured in the neighborhood of 1 quadrillion times the strength of Earth's own, the most powerfully magnetized objects known anywhere in the universe. In roughly a fifth of a second, SGR 1806-20 unleashed a gamma-ray flare with a total energy researchers calculated at around 2 × 10⁻46th power ergs, 100 times more powerful than either of the only 2 previous magnetar giant flares ever recorded, and enough energy, according to one comparison, that the star released as much power in that instant as our own sun radiates over roughly 250,000 years. The blast was so bright that it saturated most of the gamma-ray detectors pointed at it, actually measurably disturbed Earth's own ionosphere from 50,000 light-years away, and left astronomer Kevin Hurley of the University of California, Berkeley, calling it, without much need for embellishment, the mother of all magnetic flares, a true monster. Brian Gainsler, of the Harvard-Smithsonian Center for Astrophysics, who led follow-up radio observations of the flare's afterglow, put the scale of it in the plainest terms available. Astronomically speaking, he noted, this explosion happened in our own backyard, and only the Sun, and perhaps a handful of the most spectacular comets in history, have released more total energy onto Earth than this single, fifth of a second flare from a dead star 60,000 light-years away. The physical mechanism researchers now believe was responsible is a sudden, catastrophic fracture of the neutron star's rigid crust, a starquake, unleashed by the sheer torque of its own magnetic field, reconfiguring itself in an instant, converting a staggering amount of stored magnetic energy directly into light, faster than almost any other known process in the universe. From a neutron star that briefly outshone nearly everything else in the sky, to a neutron star that broke 2 separate records at once, spinning faster and weighing more than physics is entirely comfortable with. PSR J0952-0607 is a pulsar, a rapidly rotating neutron star, discovered in 2017 and confirmed through follow-up study by a team including astronomer Roger Romani of Stanford University, and it belongs to a particularly aggressive subclass nicknamed Black Widow pulsars, named for the way they slowly consume their own binary companion. J0952 spins on its axis an almost incomprehensible 707 times every single second, making it the fastest spinning neutron star known anywhere in the disk of the Milky Way, only barely edged out galaxy-wide by a single other pulsar found in a distant globular cluster. That speed alone would be enough to earn it a place on this list. But the more recent finding is stranger still. Using the Keck telescope in Hawaii to study the pulsar's tiny, nearly destroyed companion star, a substellar object, roughly 3% the mass of our Sun, being actively evaporated by the pulsar's radiation, Romani's team measured the pulsar's own mass at 2.35 times that of our Sun, the highest neutron star mass ever reliably measured, sitting right at, and arguably past, the theoretical upper mass limit most physicists had assumed neutron stars could not exceed before collapsing further into a black hole. Astrophysicist Alex Filippenko of the University of California, Berkeley, who was not part of the discovery team but commented on its significance, laid out exactly why that number matters so much. We know roughly how matter behaves at nuclear densities, like in the nucleus of a uranium atom. A neutron star is like one giant nucleus, but when you have 1.5 solar masses of this stuff, which is about 500,000 Earth masses of nuclei all clinging together, it's not at all clear how they will behave. At 2 1/3 solar masses, packed into a sphere barely wider than a city, J0952 sits precisely at the edge of that uncertainty, a genuine, still unresolved test case for how dense matter is allowed to get before the laws of physics say it has to become something else entirely. From a star quietly rewriting the definition of a pulsar, to a case that belongs on this list for the opposite reason from everything else in it, because this is the one where the prediction of something impossible turned out to be wrong. In 2017, a team led by Larry Molnar, an astronomy professor at Calvin College, made one of the boldest specific predictions in the history of observational astronomy. Studying a tightly bound eclipsing binary star system called KIC 9832227, located about 1,800 light-years away in the constellation Cygnus, Molnar's team tracked how the pair's 11-hour orbital period had been steadily, exponentially shrinking over more than a decade of archival data, pulling the two stars closer and closer together. Based on that decay curve, and drawing a direct comparison to a previously observed stellar merger called V1309 Scorpii, which had followed an almost identical exponential pattern before its two stars collided and erupted into a luminous red nova, Molnar's team announced a specific, falsifiable, and genuinely thrilling prediction. KIC 9832227 would merge and explode as a red nova, visible to the naked eye from Earth, in the year 2022. It was, for an astronomical prediction, about as close to a guaranteed headline as you can get, a rare event, on a specific timeline, that anyone with clear skies could go outside and watch unfold. Red novae themselves are a genuinely strange and only recently understood class of stellar explosion, thought to result not from a single dying star, but from the literal merger of two stars' cores inside a contact binary, releasing an outburst of light surpassed in brightness only by full supernovae, and confirmed observationally in only a small handful of cases, including V838 Monocerotis, and the aforementioned V138 Monocerotis, and the aforementioned V138 Monocerotis, and the aforementioned V38 Monocerotis, and the aforementioned V138 Monocerotis. The 2022 prediction spread quickly through both scientific and popular press, and for several years, astronomers genuinely prepared to watch it happen on schedule. Then, in 2018, a separate team led by Quentin Saucier went back through the observational record specifically to stress test Molnar's model, and found a gap in the data between 1999 and 2007, worth filling in more carefully. They tracked down previously unpublished observations of KIC 9832227, captured in 2003 by NASA's Pre-Kepler Vulcan Photometer project, originally built to search for transiting exoplanets, and compared the timing of eclipses in that data against what Molnar's exponential decay model predicted for that date. The two didn't match. Digging further, Saucier's team found the likely source of the error, a 12-hour transcription mistake in the original 1999 dataset that Molnar's team had built their entire model on, a simple typo that had thrown off the calculated timing of the star's eclipses for years afterward, and made an ordinary, non-merging binary look, on paper, exactly like one spiraling toward collision. Saucier's paper concluded plainly that the newly recovered Vulcan data does not agree with the previous exponential decay model, and that the discrepancy was large enough to reject the merger hypothesis outright. KIC 9832227, as far as the corrected data shows, is not merging in any predictable near-term timeframe after all. What causes its orbital period to keep changing in the first place remains, honestly, still unexplained. But the headline-grabbing 2022 explosion never came, and the story stands as a rare, almost refreshing entry in a list like this one. A case where the impossible claim wasn't that a star broke the rules, but that a prediction about a star turned out to be built on a typo, caught and corrected years before the sky was supposed to light up and prove everyone wrong in the other direction. Which brings us to the strangest case on this entire list, a category of star that might not burn the way every other star here does, if it exists at all. Every star we've discussed so far shines through nuclear fusion, hydrogen atoms slamming together under crushing gravity and pressure, releasing the light and heat that define what a star fundamentally is. That's not just how stars work. It's close to the actual definition of what a star is. But in 2007 and 2008, physicist Catherine Fries, working with colleagues Douglas Spolyar, Paolo Gondolo, and Peter Bodenheimer, proposed something that quietly challenged that definition at its root. What if some of the very first objects to light up in the early universe weren't powered by fusion at all, but by something else entirely? Something nobody has ever directly detected in any laboratory: dark matter. Roughly 85% of all the matter in the universe is thought to be dark matter, and scientists know it's there almost entirely from its gravitational effects, the way it bends light and holds galaxies together, without ever having isolated a single particle of it directly. One leading theoretical candidate for what dark matter actually is goes by the name WIMPs, weakly interacting massive particles, and one of their proposed properties is that they might be their own antiparticles. If that's true, then when two of them collide, they annihilate each other and release a burst of energy in the process. Fries and her colleagues theorized that inside the very first collapsing clouds of primordial hydrogen and helium, in regions of the early universe dense with dark matter, that annihilation could generate enough heat to stop the cloud from collapsing the normal way, and instead cause it to glow, not from fusion, but from this strange, invisible energy source. They named the hypothetical result a dark star. According to the models, these objects would be enormous and oddly diffuse, roughly 10 astronomical units across, cooler on the surface than you'd expect for something so massive, somewhere around 10,000 degrees, made almost entirely of ordinary hydrogen and helium, with less than 0.1% of their mass actually being the dark matter fueling them, and yet capable of growing to over 1 million times the mass of the Sun, with a luminosity exceeding 10 billion suns. For over a decade, this stayed exactly what it sounds like, an elegant idea on paper with no way to test it, because nothing in the observable universe could see far enough back in time to check. Then the James Webb Space Telescope started returning data. In December of 2022, JUICE imaged 3 distant objects, catalogued as JADES GS-Z13Z, JADES GS-Z113, and JADES GS-Z11Z, and astronomers initially filed them away as unusually bright, unusually early galaxies. That same year, a research team including Cosmin Ilya, Gillian Paulin, and Catherine Fries herself looked at those same 3 objects and proposed an alternative explanation, that these weren't galaxies at all, but individual dark stars, the first candidates ever identified. That was based on photometric data alone, essentially the color and brightness of the light, suggestive but far from proof. Then, in October of 2025, using newer spectroscopic data from JUICE's NIRSpec instrument, which reads far more detailed information out of an object's light than photometry alone can, the same research group went further and identified 4 spectroscopic dark star candidates, including one sitting at redshift 14, corresponding to a moment just 300 million years after the Big Bang, one of the earliest and most distant objects ever observed by any instrument, and by some measurements, the second most distant object humanity has ever detected, period. Fries described the milestone directly. For the first time, we have identified spectroscopic supermassive dark star candidates in JUICE, including the earliest objects at redshift 14, only 300 mir after the Big Bang. Ilya explained what these objects would actually look like if the interpretation holds up. Supermassive dark stars are extremely bright, giant, yet puffy clouds made primarily out of hydrogen and helium, which are supported against gravitational collapse by the minute amounts of self-annihilating dark matter inside them. It's worth being honest about where this one stands, because it's genuinely different from everything else on this list. Methuselah's age paradox got resolved by better measurement. SM0313's missing iron got explained by a specific, testable model of an ancient low-energy supernova. R136A1's mass got directly imaged and remeasured twice. Blue stragglers got their 2 competing mechanisms confirmed and weighted through direct observation. Boyajian's star's dimming got tested in real time and traced to dust. Betelgeuse's dimming got tracked step by step, straight through Hubble spectroscopy, from eruption to dust cloud to recovery. The zombie star of Par 30 was mapped in 3 dimensions and directly observed, still hot, still active, still there. AR Scorpius pulsations were measured, polarized, and matched directly against a known neutron star pulsar's signature. SGR 1800620's giant flare and PSR J0952-0607's mass and spin were both measured directly, repeatedly, by multiple independent instruments. S5 HVS1 was tracked, its velocity measured, its origin confirmed. KIC 9832227's predicted merger was checked against recovered data, and the specific error that caused the false alarm was pinned down. Earendel was detected, magnified, and its distance calculated, even if its exact nature as a single star is still being double-checked. Even Przybylski's star, the Thorne-Zhitkov candidate, Kafau's star, and Eta Carinae's great eruption, unresolved as their underlying mechanisms remain, are built on real, directly measured light and spectral lines that everyone agrees are actually there, arguing only over what's causing them. Dark stars are different. They remain a genuine hypothesis, a competing explanation for a handful of extremely distant, extremely bright objects that JWST has turned up, sitting alongside the more conventional explanation that they're simply very early, very massive population 3 star clusters or proto-galaxies. Nobody has confirmed a dark matter particle exists in any laboratory on Earth, despite decades of dedicated searching, which means, strictly speaking, nobody can confirm a dark star exists either. But the researchers behind the idea point out that if it's real, it could solve 2 other stubborn puzzles at once: why JWST keeps finding galaxies at the edge of the observable universe that look brighter and more massive than early universe models predicted, and why some supermassive black holes appear to have formed too quickly and grown too large for their age. A collapsing dark star, and the black hole its remnant might eventually leave behind, is one candidate answer to both. So that's 18 stars, 18 separate ways the universe has managed to look, at least for a while, like it was breaking its own rulebook. A star whose calculated age briefly exceeded the age of everything walked back not by rewriting physics, but by remeasuring a distance more carefully. A star built from the wreckage of one of the very first stellar deaths in cosmic history, carrying almost no trace of the iron that should have marked it. A second ancient star, missing an entirely different set of ingredients that scientists themselves named, in print, a star that should not exist. A star so massive it blew past the accepted ceiling on stellar formation, and a companion case right next door, sitting so close to its own physical breaking point that it already blew a decade's worth of mass into space just to survive its own brightness. Stars that stay artificially young by quietly feeding off a companion, or by colliding outright, hiding in plain sight, inside clusters of stars 12 billion years their senior. A star carrying radioactive elements that shouldn't be able to survive on any stellar surface, explained by either an invisible neutron star nobody can find, or elements heavier than anything physics has ever confirmed exists. A star that might be hiding the crushed core of a dead neutron star inside its own body, a claim made, challenged, and still not fully settled a decade later. A star whose flickering got strange enough that serious scientists floated the idea of an alien civilization before the real answer turned out to be an uneven ring of ordinary dust. The single most famous star in the sky, dimming so sharply it had astronomers bracing for a live supernova. Before the real cause turned out to be a cloud, the star coughed up itself. A dead white dwarf star, spinning and blasting out beams of radiation, exactly the way only a neutron star was supposed to be able to, quietly rewriting the definition of a pulsar. A neutron star that, in a fifth of a second, outshone almost anything else the universe had to offer that day. Another neutron star, spinning over 700 times a second, while carrying more mass than the laws of physics are entirely comfortable allowing. The single most distant individual star ever caught by human eyes, visible only because the gravity of an entire galaxy cluster happened to focus its light like a lens, arriving here 12.9 billion years after it was emitted. A star flung out of the galaxy entirely by a supermassive black hole roughly 5 million years ago, moving so fast it will never come back. A pair of stars confidently predicted to collide and explode on a specific date, and called off years in advance once a 12-hour typo in the original data was finally caught. And a category of star that might not run on fusion at all, that might instead be glowing from the annihilation of a substance nobody has ever directly touched, sitting right now at the very edge of what any telescope has ever managed to see, 300 million years after everything began. What ties all 18 of these together isn't really the impossibility. Every one of them turned out to be explainable, or at least explainable in principle, once astronomers had better tools, better data, and enough patience to keep looking, and even the ones still unresolved are being chipped away at, year after year, by people who refuse to just leave the anomaly alone. What ties them together is what they say about how science actually handles the moment something doesn't fit. Nobody threw out the Big Bang because one star's age briefly didn't line up. Nobody assumed the laws of stellar death were wrong because one white dwarf refused to finish dying. Nobody rewrote the rules of stellar evolution the first time a blue straggler showed up, looking decades too young for its neighborhood. And when the data behind a headline-grabbing prediction turned out to rest on a single mistyped number, nobody buried that either. They published it, corrected it, and moved on. The response, nearly every single time, was the same. Look closer, measure again, build a better instrument, and let the universe explain itself on its own terms. Some of these mysteries took 20 years to close. One of them, the Thorne-Zitkov candidate, is still sitting in genuine limbo more than a decade after the original claim. CAFO's star has sat unresolved for even longer than that. Another, the Dark Stars, might not close for another 20 years, if it closes at all. But that's what's actually out there, quietly, all the time, whether we're looking or not. Stars older than they should be. Stars made of almost nothing, in more than one way. Stars too massive, and stars too bright for their own good. Stars that feed on their neighbors to stay young. Stars carrying elements that shouldn't survive. Stars that might be hiding a dead star inside themselves. Stars that fooled us into thinking about aliens or a supernova before settling for something far more ordinary. Dead stars, acting like they're not dead at all, some of them spinning faster and weighing more, or flaring brighter for a fifth of a second than physics is entirely comfortable with. Stars so far away, their light left before most of the universe's structure had even finished forming. Stars running from black holes. A collision that got called off. And stars that might be burning on something we can't even name yet. If any part of that got under your skin a little, that's the whole point of putting a list like this together. And if you want more of it, the subscribe button is right there, so you don't miss the next one.